You may have heard the word surd being thrown around pretty often in a maths class, but you might not know what it is. So in this lesson, I'm going to explain exactly what a surd is and exactly why we should learn about them. It turns out that surds are born from the index laws, so you should already know a little bit about the index laws first. So watch the video on the index laws if you don't know anything about them. But we know that 2 cubed is going to be the exact same thing as 2 times 2 times 2. And yes, I use dots for times, but that's pretty common, so just know that this means times. But then if 2 cubed is going to be 2 times 2 times 2, well then 2 to the power of 4 is actually going to be 2 times 2 times 2 times 2 one more time. So now I have a puzzle for you, one that was faced by the ancient Greeks and many people before them. What is 2 to the power of 3.5 going to equal? Now this is the part in the video where I really suggest that you pause and try to figure out exactly how to calculate 2 to the power of 3.5. I mean, if 2 cubed is 2 times 2 times 2, and 2 to the 4 is 2 times 2 times 2 times 2, then what should 2 to the power of 3.5 actually equal? Now if you did actually pause it and try, welcome back. But if you didn't, let's actually go ahead and think about what 2 to the power of 3.5 should equal. So to figure out what 2 to the power of 3.5 should actually equal, we can start by actually using the index laws. First off, we know that 3.5 is the exact same thing as 3 plus 0.5. Once we know this, then the index laws say that this can be rewritten as 2 to the power of 3 and then 2 to the power of 0.5. So now at this point, I want you to realize that 2 cubed is something we already know how to calculate. It's just the same thing as 2 times 2 times 2, which we've already said. Now 2 times 2 is 4, and then 4 times 2 is just 8. So that means this 2 cubed is the same thing as the number 8. So then I guess the real difficulty lies in calculating this number over here, which is 2 to the power of 0.5. So I've written here that if we want to calculate the value of 2 to the power of 0.5, so we can multiply this 8 by it, then the index laws are actually going to come to the rescue one more time, because there's something simple that we can write that will help us calculate this value. We have another index law that tells us that if we have something in this form over here, then we can multiply this number and this number to produce a new index. Now, if the left-hand side is the exact same as the right-hand side, well, then we know that 0.5 times 2 is the same thing as the number 1. But we don't really need to write 2 to the power of 1 as 2 to the power of 1. We can just leave the 1 off. And now we've come to the most important point of the day here. If we want 2 to the power of 0.5, then 2 to the power of 0.5 is a number that when squared gives you the number 2. So we're looking for a number that if we square it, we get the number 2. Now the way I'm going to try to actually find the value is by squaring a bunch of numbers and then looking in between the gaps. Now we know that the value we're after is not the number 1, because 1 squared is actually the number 1. And the value is not going to be 2 either, because 2 squared is 4. We're after a number that when squared gives you the number 2. The number 1 squares to 1 and the number 2 squares to 4. So the number we're after has to be somewhere between the numbers 1 and 2. Now, squaring a number is actually something that's pretty easy to do. All we need to do is we need to multiply this number by itself to get the one below it. If we wanted to try another number between, say, 1 and 2, like 1.5, multiplying 1.5 by itself is no harder, but it's going to take a little bit longer. So I'm going to pull out a calculator to help us with those calculations. So to find the square of 1.5, we just type 1.5 times 1.5 into our calculator. So the square of 1.5 is 2.25. Now the number we're looking for squares to 2, so 1.5 is definitely not the correct number. In fact, it's too high, because 1.5 times 1.5 gave you a number bigger than 2. So we should try a number a little bit smaller than 1.5. So how about we try 1.4? Now, after this point, we see that 1.4 actually squares to give us the number 1.96. Now 1.96 is too small to be the number 2, so therefore the number we're after is a little bit bigger than 1.4, but a little bit smaller than 1.5. So now that we've expanded our number line, we can just continue this process for as long as we like. How about we try the number over here, right in between 1.4 and 1.5. That would be the number 1.45. So after calculating this, we see that 1.45 squared is actually the same thing as 2.10. Now 2.10 is bigger than the number 2 that we're after, so we should use a smaller number than 1.45. So how about we try 1.42? And now we still see that 1.42 still doesn't square to give us the number 2. This time 1.42 is 2.01. It's really close to 2, but it's not quite 2, so we have to keep going. Now, it's actually larger than 2, so we have to try a smaller number. So let's try 1.41 this time. Now we see that 1.41 squared is approximately 1.99. And this is definitely the point where you should throw your hands up in frustration, because this really feels like it's going to go on forever. So your feelings of frustration are actually totally warranted, because there is no number that will ever square to give you the number 2. However, by continuing this process for as long as we like, we will eventually get to a number that looks so close to 2 that it's basically indistinguishable from the number 2. So, in a final act of desperation, we define 2 to the power of 0.5 to be the square root of 2. Now the square root of 2 is the number that you seem to approach as you continue this process forever. So at this point, we need to make a definition. This symbol over here is what we call a radical. And if you're at the radical of 2, then we're saying we're looking for the number that squares to give you the number on the inside. So we would say that this number over here represents the concept of the square root of 2. But I want you to understand that you could continue doing this process forever and you would never quite reach the square root of 2. So at this point, we've completely answered our question from before. 2 cubed is 2 times 2 times 2. 2 to the 4 is 2 times 2 times 2 times 2. But 2 to the power of 3.5 is calculated by first multiplying the number 8 by 2 to the power of 0.5. But unlike 2 to the power of 3 and 2 to the power of 4, which can be calculated explicitly, 2 to the power of 3.5 needs to be calculated by repeating this process for a really long time, until you have the desired precision that you're after. So we're going to define the square root of 2 as 2 to the power of 0.5. And if we continued this process for a whole afternoon, then eventually we would get this number over here. The square root of 2 is approximately equal to 1.414213,562. And then we write, and so on. Now this and so on business over here just tells us that we could continue this process down here to get even more digits if we were so inclined. Remember that 0.5 is also the same thing as 1 on 2, so we can also write this as 1 on 2. And so finally, the square root of 2 is the same thing as 2 to the power of 1/2. Now, if this is such a good approximation to the square root of 2, how about we try squaring it? So even after squaring this number here, which is very, very close to the square root of 2, when we go ahead and actually square it, we get 1.99999, and then you get 8 nines, but then you get an 8945. So you do not get the number 2. Just to show you how close we actually are, how about I replace that 2 at the end for a 3, and then we can see what happens then. So the last number was slightly smaller than 2, but by changing this 2 to a 3, now the number is ever so slightly larger than the number 2, and that's actually pretty interesting. So this approximation to the square root of 2 is the closest number we can get that squares to give you 2. But, of course, you need to continue this process forever to actually get to the number that squares to give you 2. Now, as you saw, to find a number that squares to give you the number 2, you need this long, infinite process, and therefore, you're never actually going to find such a number. You can get as close as you like to that number, but that number just doesn't exist. And therefore, we would say that the square root of 2 is absurd. That's right, the word absurd sort of sounds like the number surd, and that's because they come from the same place. To be clear about what I actually mean here, writing down the value of a surd, the exact value, is totally absurd. And that's the reason why we call these things surds. And the reason it's absurd is because surds are the simplest example of what we'd call an irrational number. Now, in the lesson on numeric sets, I did explain the idea of a rational and an irrational number. There are two different ways to think about the set of rational numbers, which I've drawn over here. The first way is that you can think of it being some number divided by another number, where both of those numbers are integers. But I think the more useful way for this particular discussion is to think about the idea that you could always write this number as a repeated decimal. So, for example, the number 17 on 26 is the same thing as 0.653846153 and so on. Now, when we say and so on over here, this is actually very different to when we set it up here, because we know that these digits are just going to repeat over and over again. So once we've gotten to this digit over here, we can technically say that we're done calculating, because we know that we're just going to do 5384, 5384, and so on. So if you think about it, if we know all of the digits by just looking at these ones over here, then all of this on the right hand side is totally unnecessary. We would call this the period of the rational number, and for this case there's 1, 2, 3, 4, 5, 6 digits in the period. But for a larger rational number, the period is actually not so easy to determine. For a number like 173 on 295, if you wrote out the digits, you'd get 0.58644, and you could keep writing out digits all day. If you tried to find the period, however, you'll find that the period is actually 58, so you need at least 58 digits to see the pattern. I'm not going to explain how I found this number of 58, but I might do that in a follow-up lesson later on. But the main idea is that every single rational number has a particular period, and you only need to calculate a few digits to calculate the whole rational number. So then this brings us to the square root of 2. Is the square root of 2 a rational number, or is it not a rational number? I mean, after all, this number over here needed 58 digits, and I didn't even write 58 digits for the square root of 2 anyway. Now it turns out, and I'm going to prove this in a follow-up lesson, that the square root of 2 is actually not rational. It is totally impossible to write the square root of 2 as a rational number, and therefore it does not belong inside this set. And this would explain to us why we call surds irrational numbers. They're irrational because they are not rational. Now, we've talked about the square root of 2 in a lot of detail here. And in fact, you can of course take the square root of 3, the square root of 4, the square root of 5, or whatever you wanted. You can repeat these exact same steps if you like for the square root of 3, for example, and you can try to find its digits as well. But there's nothing really special about this particular problem where we're raising things to the power of a half. In general, a surd is any number we raise to any fractional power, rather than just 1/2. For a general surd, we write the 8th root of b, which is the same thing as b to the power of 1 on a. If ever you see this a left off, which it will be many times when you see it, you assume that this is the square root, so you assume that a actually equals 2, as it did up here. If, for example, in this expression up here, the 2 was a 3 instead, rather than looking for a number that squares to give you 2, you're looking for a number that cubes to give you 2. So how about I just give you some examples to see this in action? So in this problem, I'd like to find the exact values of the 3rd root of 8 and then the 10th root of 4 to the power of 5. Feel free to actually hit the pause button and try both of these yourself, and then you can unpause and watch how I do it. In this problem, we can see that a is the same thing as 3, and b is the same thing as 8. Therefore, I can rewrite this as 8 to the power of 1 on 3. So therefore, the cubed root of 8 is the same thing as 8 to the power of 1 on 3. Now, you may or may not realize this, but 8 is also the same thing as 2 cubed, because 2 times 2 is 4, and then 4 times 2 is the number 8. So let me replace 8 for 2 cubed. So that means 8 to the power of 1/3 is the same thing as 2 cubed, all to the power of 1 on 3. But now we can use the index laws, so we can multiply this 3 by this 1 on 3. and that's going to give us the number 1. And of course, we don't really need to write that 1, so I can just get rid of it. So therefore we can see that the cubed root of 8 is the same thing as the number 2. Now that makes sense because 2 times 2 is going to be 4, and then 2 times 4 is going to be 8. So 2 multiplied by itself 3 times gives you the number 8. So now for the next problem, I'm going to do the exact same thing. Instead of writing this as the 10th root of 4 to the power of 5, I'm instead going to write this as 4 to the power of 5 all to the power of 1 on 10. Now after this, I can go ahead and multiply this 5 by this 1 on 10, just as I did before. And now 5 on 10 is the same thing as 1/2, so we might as well replace that as well. Now as we know, 4 to the power of 1/2 is going to be the same thing as the square root of 4, so we can also rewrite this as the square root of 4. And then we're just looking for a number that when multiplied by itself gives you the number 4. Now of course that number is 2. 2 times 2 is the same thing as 4. And therefore we can also say that the 10th root of 4 to the power of 5 is the same thing as all of these things, but it's also the same thing as the number 2. Now you can do as many exercises like this as you like, but one of the main ideas is that you want to convert surds into their fractional form, and then you just go ahead and use the index laws to make things as easy as you possibly can. But that just about completes my examples, and I just want to say one more thing before I finish up. So the last thing I want to say is that surds have no pattern in their digits. I've already said that a few times, but rational numbers do have patterns. Now because rational numbers have patterns and surds don't have patterns, then it's actually impossible to mix surds and rational numbers to make one single number. Now for example, I've got this number 3, which is an integer, and then I've got 2/3, which is a rational number. Now the whole idea is that you can mix an integer and a rational number to make a single rational number. Now the process to do this has been explained in the lesson on simplifying fractions, but I could rewrite this 3 as 9 on 3. And then after that, I just add the 9 and 2 to get 11 on 3. So that immediately shows us that we can mix an integer with a rational number to make another rational number. But this is not true for surds. So we've said that integers and rationals mix together to make new rationals, but integers and surds do not mix at all. So therefore, anytime you see something like 3 plus the square root of 2, you can't simplify it any further. You just leave all the integers, the rationals and all of those on one side, and then you leave the surds on the other side. They just don't mix. And for another fun fact, surds don't even like to mix with each other, unlike rational numbers. So for example, if you had the square root of 2 and the square root of 3, you usually can't rewrite this as a single surd. But at this point, I'd just like to go ahead and summarize the lesson. In this lesson, we explained what surds are and why we need them. Without surds, we cannot calculate the values of simple expressions like 2 to the power of 3.5. We found that in order to calculate 2 to the power of 3.5, you eventually ended up with something in the form of 2 to the power of 0.5, and we needed to find the value of that. We said that 2 to the power of 0.5 is just going to be a number that squares to give you the number 2. We started a long and pretty arduous process, but in the end we were able to show that this number is between 1.41 and 1.42. We said that if you continue this process forever, you can generate as many digits of the square root of 2 as you like, but no matter how long you keep going, you are never going to run out of new digits to generate. So unlike rational numbers, where they have an actual period, and that means you can stop at some point, surds do not have patterns, and to actually have the value of a surd, you technically need an infinite number of digits, and that is absurd. We also said that you can write a general surd in this form over here, and that's the same thing as b to the power of 1 on a. And finally we said that surds do not mix with rational numbers, so if you have an expression like 3 plus root 2, you can't simplify it any further. So now the next question is, where do we go from here? Well, I mentioned during the lesson that the square root of 2 is actually an irrational number, and that's probably something I should prove to you, because after all, a number like 173 on 295 has a period of 58, and I'm not going to go writing out 58 digits to show you that it's actually irrational. In fact, you can easily write down a rational number that has periods in the thousands, So how do we know that the square root of 2 is not just a rational number with a really large period? So in an immediate follow-up lesson, I will actually prove to you that the square root of 2 is in fact irrational, and it does not belong inside the set of rationals. But then beyond there, we actually need to learn to incorporate surds into our algebra, and that's something I'm going to show you in a future lesson. But at this point, I'd like to complete this lesson on introducing surds. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.